This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we're delving into a fascinating paper titled UAVs Meet LLMs, Overviews and Perspectives Toward Agentic Low-Altitude Mobility. This paper explores the integration of large language models, LLMs, with unmanned aerial vehicles, UAVs, aiming to significantly enhance UAV autonomy and capabilities. Let's start with the core argument. Why is this integration of LLMs and UAVs so significant?
The current limitations of UAVs primarily stem from their reliance on human control, restricting their autonomy and adaptability in complex environments. LLMs, with their advanced reasoning and generalization capabilities, offer a powerful solution to overcome these limitations. The integration promises to create UAVs that are more intelligent, adaptable, and capable of handling complex tasks autonomously.
The paper provides a systematic overview of UAV systems. What are some of the key functional modules highlighted and how do they interact?
The paper details several key modules: perception, using various sensors; navigation, position and trajectory control; planning, mission-to-flight path translation; control, actuator commands; communication, data exchange; human-drone interaction, user interfaces; and payload, mission-specific equipment. These modules interact in a complex, interconnected manner, with information flowing between them to achieve the overall mission objectives. For example, the perception module feeds data to the planning module, which then generates a trajectory for the navigation and control modules to execute.
The paper also discusses different embodied configurations of UAVs. What are the main types and what are their respective strengths and weaknesses?
The paper categorizes UAVs into fixed-wing, high-speed, long endurance but cannot hover; multi-rudder, versatile, VTOL but limited endurance; unmanned helicopters, high payload, good wind resistance but slow; hybrid, combining fixed-wing and multi-murder advantages; flapping wing, bio-inspired, quiet, maneuverable but low payload; and unmanned airships, cost-effective, quiet but low speed and maneuverability. Each type is suited to different tasks based on its unique characteristics.
The paper then moves on to foundation models, specifically LLMs, VLMs, and VFMs. Can you summarize the key capabilities of these models and provide some examples?
LLMs excel at natural language understanding, generation, and reasoning. Examples include GPT, Claude, and Llama. VLMs combine visual and textual information, enabling tasks like visual question answering (VQA) and image captioning GPT-4V, LLALL. VFMs focus on extracting visual features for downstream tasks, such as object detection and segmentation (CLIP Dino SAM). These model strengths lie in their generalization, zero-shot learning, and multimodal capabilities.
This paper emphasizes the importance of datasets and simulation platforms. What are some key datasets and platforms mentioned, and what roles do they play in advancing this research?
The paper lists numerous datasets categorized by task: environmental perception, event recognition, object tracking, action recognition, navigation, and domain, transportation, remote sensing, agriculture, etc. These datasets provide crucial training data for the models. Simulation platforms like AirSim, Carla, and NVIDIA Isaac Sim offer safe and controlled environments for testing and validating algorithms, generating synthetic data, and reducing the cost and risk associated with real-world testing.
The paper proposes a framework for agentic UAVs. Can you describe the key components of this framework and how they interact?
The Agentic UAV framework consists of 5 modules: data, preparing data for FM training; knowledge, domain-specific information; tools, general and task-specific tools like VFMs and flight controllers; FM, the chosen LLM or VLM; and agent, workflow for perception, planning, and action. These modules work together, with the agent module orchestrating the process, using the FM for high-level decision-making, the knowledge module for context, and the tools module for specific tasks. A manager agent coordinates multiple UAVs in a swarm.
The paper explores several application scenarios. What are some key examples of how FM-enhanced UAVs are being applied?
The paper highlights applications in surveillance, traffic monitoring, urban patrolling, logistics, delivery, route planning, and emergency response, disaster relief, communication network establishment. In each case, the integration of FMs enhances perception, decision-making, and human-machine interaction, leading to more efficient and autonomous operations.
What are some of the key challenges and future research directions identified in the paper?
Challenges include ensuring robustness and reliability in real-world conditions, addressing potential biases in training data, managing computational resources, and ensuring safety and ethical considerations. Future research should focus on improving model generalization, developing more efficient architectures, and exploring new applications in diverse domains. The development of robust, reliable, and safe agentic UAVs is a key focus.
The paper concludes by emphasizing the potential of agentic UAVs, what are the key characteristics of an agentic UAV, and what are the implications of this technology?
Agentic UAVs are characterized by their ability to autonomously perceive, reason, plan, and act in complex and dynamic environments. They leverage FMs for advanced cognitive capabilities, enabling them to handle unforeseen situations and adapt to changing conditions. The implications are far-reaching, impacting various sectors, from logistics and surveillance to environmental monitoring and disaster response. The potential for increased efficiency, safety, and autonomy is substantial.
Paper mentions several specific methods and models used in existing research. Can you highlight a few examples of how these models are being integrated into UAV systems for specific tasks?
Several examples are given. For object detection, models like CLIP and grounding dyno are used to improve accuracy and robustness. In vision language navigation, VLN, models like LLALL and GPT-4V are employed to enable drones to navigate based on natural language instructions. For planning, LLMs like GPT-4 are used to generate mission plans from natural language descriptions. In flight control, LLMs are being explored to enable natural language-based control of both single UAVs and swarms.
The paper also discusses the importance of data modules in the Agentic UAV framework. How are datasets being adapted and created to support the training and fine-tuning of these foundation models for UAV-specific tasks?
The data module focuses on adapting existing datasets or creating new ones suitable for fine-tuning FMs for UAV tasks. This involves converting sensor data, images, videos, LiDAR, etc., into formats compatible with LLMs and VLMs, often by generating natural language descriptions or question-answer pairs. The goal is to create datasets that reflect the complexities and nuances of real-world UAV operations.
The paper highlights the role of the knowledge module in the Agentic UAV framework. How does the integration of retrieval, augmented generation, enhance the capabilities of system?
The knowledge module using RAD allows the system to access and integrate relevant information from external knowledge bases. This enhances the accuracy and reliability of the FM's outputs by providing context and mitigating the risk of hallucinations. For UAVs, this means accessing real-time data, weather, air traffic, etc., and domain-specific knowledge, airspace regulations, etc., improving decision-making and adaptability.
The paper emphasizes the tools module within the Agentic UAV framework. What are the key general purpose and task-specific tools that are integrated into the system?
General purpose tools include VFMs like CLIP, SAM, and grounding dyno, which handle various visual tasks. Task-specific tools include flight controllers like PX4 and PicHawk, providing low-level control and mission planning capabilities. The combination of these tools provides a flexible and efficient system capable of handling diverse tasks.
The agent module is a crucial component of the proposed framework. Can you elaborate on the roles of the manager agent and the UAV-specific agentic workflow?
The manager agent coordinates the actions of multiple UAVs in a swarm, handling high-level task allocation and overall mission planning. The UAV-specific agentic workflow involves a sequence of agents, perception, planning, control, that process data and execute tasks autonomously. This combination of global coordination and individual autonomy is key to efficient and adaptable swarm operations.
The paper mentions the importance of agent collaboration and adaptability within the swarm. How does this interaction enhance the overall performance and robustness of the system?
Collaboration allows UAVs to share information and coordinate their actions, improving efficiency and robustness. For example, UAVs can share sensor data to avoid collisions or collaborate on complex tasks. Adaptability allows the swarm to respond to changing conditions and unforeseen events, ensuring mission success even in dynamic environments.
The discussion of the paper has covered a wide range of topics. Let's revisit the core contribution of the paper. What is the main takeaway for experts in the field of UAV and LLM integration?
The paper's main contribution is a comprehensive overview of the current state of the art in integrating LLMs with UAVs, providing a systematic frame for developing agentic UAVs. It highlights the potential of this integration, identifies key challenges, and proposes future research directions, serving as a valuable resource for experts in the field.
The paper extensively covers various datasets. Can you elaborate on the significance of these datasets in the context of training and evaluating LLMs for UAV applications? What are some of the challenges in creating these datasets?
The datasets are crucial for training and evaluating the performance of LLMs in UAV-related tasks. However, creating these datasets is challenging. It requires significant effort in data collection, annotation, and ensuring data quality and diversity. The datasets need to represent the complexities and variations of real-world scenarios, including diverse weather conditions, lighting, and object appearances. Furthermore, annotating data with natural language descriptions requires expertise and can be time-consuming.
The paper delves into the optimization of foundation models for UAV-specific tasks. What are some of the key techniques used for model optimization, and how do they address the challenges of adapting general-purpose models to specific UAV applications?
Key techniques include instruction fine-tuning, prompt engineering, and the use of techniques like LoRa for parameter-efficient fine-tuning. These methods address the challenge of adapting general-purpose models to specific UAV tasks by tailoring the model's training data and input prompts to reflect the specific requirements of the application. This allows for improved performance and efficiency without requiring extensive retraining from scratch.
The paper discusses the integration of various foundation models into UAV systems for different tasks. Can you provide a more detailed comparison of the strengths and weaknesses of using LLMs versus VLMs versus VFMs in different UAV applications?
LLMs are best suited for tasks requiring high-level reasoning, decision-making, and natural language processing. VLMs are ideal for tasks involving both visual and textual data, such as VQA and image captioning. VFMs excel at extracting visual features for tasks like object detection and segmentation. The choice of model depends on the specific task and the type of data involved. Often, a combination of these models is used to leverage their complementary strengths.
This has been a third discussion of the paper's key findings and implications. Thank you for your insights.